Hello, in this video, we're going to be talking about optimization, which means we're trying to use our knowledge of minimum and maximum values and apply them to contextual problems. There are a series of steps that we can follow in order to make this process a little bit easier. So in this problem, we're trying to figure out what is the closest this point gets to this curve. So it's recommended to make a quick sketch and say, okay, well, we want whatever this line to be as minimum as possible, because as we go to different spots on our curve, we get different lengths of that line. Then figure out what we want to maximize or minimize. We want to minimize or maximize our distance formula. Next, our goal is try to get this down to have a single variable, because right now we got D, we got X2, we got X1, we got Y2, we got Y1, we got too many things going on. So our goal is to narrow that thing down. So we can plug in our point that we got, and we can kind of plug in that idea of X is Y squared, our Y value is X squared. And then we can do a little bit of simplification in here in order to get something that will be a little bit easier to find the derivative of, because that is almost our next step. First, we got to figure out what would make sense for our problem. I want to make sure that our distances are only going to be positive. So if we get any sort of negative values out of this, I'm not going to trust that. Now we're going to find the minimum or maximum values with calculus. And then here is me going through doing that. I found the derivative of this thing, did a little bit of cleanup with it. Then I wanted to figure out when that derivative equaled 0. So it equals 0 at this single point. I know that this is going to be the minimum distance for a couple reasons. One, kind of looking at my diagram, that's going to be about right here. And then anything else, like if I got another value, would be very, very far away. So in fact, there will be no maximum. It'll continually to get farther from that point. Or I can also think about what's going to go on with this derivative on either side of 1. If I put in some value a little bit bigger than 1, I'm going to get a positive value up here. So overall, I'm going to get a positive value. And then if I put in some number that's smaller than 1, like 0, I'm going to get a negative value. So I've got a function that's decreasing and then increasing. And if I'm decreasing and then increasing, that means that has to be a minimum value by the first derivative test. In this next example, I've got a box that we're going to cut out based on this sheet of cardboard, and I drew a picture of the corners we're going to cut out of that box. So we want to figure out what the dimensions of the box of largest volume we can make and what its volume is going to be. So I need a volume equation. So volume is length times width times height. So I'm going to write that. I've got my drawing already, and now I got to get my equation. So volume equals length times our width times our height. But that is like 3 separate variables, and I don't like that. I want to try to get it so we just have one of those variables. We need to turn that length, that width, and that height all to be the same thing. That sound good, Mel? Here we go. Our height is going to be, as we kind of fold up those edges, that is going to be our x value. Whatever our x ends up being, that will be the height of our box. So that is x. Our width is going to be along this side down here. So it's whatever the width of our box is. And this side is 8, and this is 15. They told us that up top. So our width is going to be 8, but it's going to take out 2 of those x's. So our width is 8 minus 2 of our heights. Same thing's going to happen with our length. It's going to be 15 minus 2 of our heights. That is going to be the volume of our box. Now, in terms of what sort of values are we looking for, I am looking for just positive values, and I should keep it between 0 and 4. It should be a little bit bigger than 0, but if it's at 4, at that point, I've cut out this whole side. So I should get values between 0 and 4. So it is time to take derivative. I'm going to clean up this problem a little bit, though, before I take derivative by multiplying all of that. A FOIL and in a distribution later, I end up with this, which is going to be a lot easier to find the derivative of than if I were to try to do a product and a product rule. Ugh, that doesn't sound like fun. So V prime is going to be 12x squared minus, let's see, that is going to be 92x plus 120. So now I need to figure out when this thing equals 0. Little solving later, I get x equals 5/3 and x equals 6. Now, if we remember from earlier, 6 is going to be too big. If I cut out a 6 by 6 square on each side, that's cutting out, that's going to be 6 and 6. That's too big for that 8. So 6 is not going to be a reasonable choice. That 5/3 is between 0 and 4, so that should be good. I do care about whether or not that is a maximum or a minimum value for my box at that point. So let's take a look at the second derivative in order to make that determination. I found my second derivative. It's 24x minus 92, and then I plug in that 5/3. So that's 40 minus 92, which is negative 52. That is less than 0. Since I have a negative value for my second derivative, that means I'm concave down at that point, and that 5/3 by the second derivative test is a maximum value. This is how big of squares we need to cut out from our corners of the box. So then it's just a matter of taking this 5/3 and plugging into these two places. I've done that off camera. We get a box that's 5/3 of an inch by 14/3. That's 8 minus your 2 5/3. And then 35/3. That's the 15 minus 2 5/3. So that'll be the dimensions of our box. And its volume will be this times this times this, which is 2,450 27ths of an inch stuff. Yeah, you could probably make those decimals, but I wanted fractions, so I kept them as fractions. And that's it. Done. In this example, we're looking for a minimum area. We've got this paper. We got 30 square inches to print on, and it's a rectangular paper, and there's a 1-inch margin. Make a little paper? How little make paper? Okay. So we've got to figure out what is this thing's area. So the area of the paper is just its length times its width. But its length and its width is dictated by the area of the paper. The area is the length of the paper plus 2 for that 1-inch margin. And then the width of the paper plus another 2 for the 2 inches on either side. So that's narrowing it down, but well, not really. We have the same number of variables, but at least now we're kind of incorporating those 2 inches. What about those 30? So the 30 is the area of the paper. So I'm sorry, the area of the printing is just length times width, and we know what this area is. It's fixed at 30. Using that idea, we can say, hey, actually, we can rewrite that L and W. Let's make them both W's. So we can say L is the same as 30 divided by W. So I can replace this L here with this 30 divided by W. Here I've done that, and then I did a little bit of simplification. I did a FOIL and then combined my like terms. I also turned the 60W to the -1 from this 60 over W, so I don't have to quotient rule. Now, what numbers are going to make sense for what we're doing with this W? I want to make sure that whatever I get, I want to make sure that those values are going to be positive because I want a positive length and width for my paper. But beyond that, I think we should be fine. We just want to make sure that we get positive values. W needs to be greater than 0. So now I want to figure out what A prime is going to be. So my derivative is going to be 2 minus 60 W to the -2. Now that I've got my derivative, I care about when that derivative equals 0 because that'll tell me my critical points and when I get a maximum or minimum value. So 2 minus, I'm going to make this 60 over W squared equals 0. Subtract that 2 from both sides. So we get -60 equals -2, and multiply both sides by W squared, so we get that thing out of the denominator. Then we divide both sides by -2, and W equals plus or minus the square root of 30. Now, we said earlier, we only want positive values for that width because we're talking about the width of a piece of paper. So we don't care about the negative square root of 30. We do care about that positive square root of 30. Now, I also care about, is that going to be the minimum value? If that negative 30 is our minimum value, we're going to be in trouble. So we got to check that positive value. So let's see what's going on at a double prime to determine that. So its derivative will be 60 w to the negative 30. And if we put in so this is 60 over w cubed. If we put in that cubed root of 30, we're going to get some positive value. So at w equals square root of 30, a double prime is going to be a positive value. Since it's a positive value, that means we are concave up at that point, and we're going to get a minimum value out of this function there. So our first derivative is 0, our second derivative is positive, so that must be a minimum value, and that's what we wanted. Now that we know what W is, we can go back up here and figure out what L is going to be. Well, it's something times the square root of 30 is 30, so L is also going to be the square root of 30. So we've got just that rectangular page is going to end up becoming a square page. Sorry, that's how we get this minimized. So L is also the square root of 30. Now remember, that length and width that we found is based on the area of the printing. It is not the dimensions of the paper. We want the dimensions of the paper. We want this thing's L and W, and we just found the blue L and W. So we just got to add 30. So our paper should be stuff. All we need to do is add on that plus 2. So the paper should have a length and width of square root of 30 plus 2 inches. That is the end of our video on optimization. So reminder, make those sketches. They are really helpful. Get your equation down to a single variable and determine what the good values that make sense for your problem. You don't want to be producing negative desks or making half of a teddy bear. Or cutting a box into too small of pieces. After you've done that, then start maximizing and minimizing using our first and second derivative tests to determine whether you found the maximum value or the minimum value. Thanks for watching. Hope you took excellent notes, and see you next time. Bye-bye.